Hey, everybody out there in the Global Hack Week world. How are we feeling on the very last day of Global Hack Week? Awesome. Well, welcome for this next workshop. This is going to be our last one for the machine learning. We've had some awesome people joining us for the workshops, and it's been a great ride. So let's finish strong, right? We'll finish strong with um, some of these concepts. So let me go ahead and share my screen. Um, Grab our slides for the day. Yeah, there they are. So today we're going to be talking about linear regression and Python. And this is part two of our machine learnings for that. So make sure that you check in. It's actually part three, I guess. I have a little bit of a mistake on there, but this is our check-in link for the event. So go ahead and make sure you're checked in. It's important for us to know, who's interested in these types of events, and who is what kind of content should we be bringing you. But it also gives you the chance to check in for swag, so you can actually get some swag. So definitely take advantage of that. And let me give you all a brief introduction. My name is Steven. I work with Major League Hacking on many different teams, on our admissions team, also doing hackathons, and especially Global Hack Week for this week. And so I've been doing that for over 6 years now with the team, and I'm really excited to be here today. So here's some objectives that we have for the day. They are to understand the classification techniques in machine learning. So we'll talk a little bit about how they're classified, learn about some decision trees and k-nearest neighbor algorithms. So those are going to be really cool. We're going to actually deep dive into those in our code, and then implement some classifiers and evaluate their performance. And we'll even solve some practical problems using these algorithms. So there's a ton of stuff on the agenda, and we will get started with it. But last time, I want to talk about what we did. We covered the basics of machine learning regression, which was linear regression. That's where we left off. And now we'll cover classification, which is going to be two major algorithms: decision trees and k-nearest neighbors. And they're really powerful tools for making predictions about categorical data. Um, and by the end of this workshop, you'll learn how these algorithms work. You'll implement them in Python, and you'll apply them to real-world data sets. So that'll be really good. All right. And next, wanted to talk to you about the basics of classification. So classification is a supervised learning technique. So remember, we talked a little bit about the differences between supervised, unsupervised learning. And we will be doing this, which is a supervised learning technique. So it's involving labeled data, human labeled data. For example, email spam detection. You could tell the algorithm what email is spam, what email is not. You could tell it about disease diagnosis, so it could diagnose someone's illness. And image recognition, so maybe it could just say, based on a list of images that are hand labeled, what is this an image of? So we did look at the Cypher 10 data set last time. Let me show you that all again. for those of you who weren't here for that, because it's kind of a cool data set. Show you here. So you can see these are all the images in the Cypher-10 data set, and you can tell that students were actually paid at the university to label these images. So that's an example of supervised learning data set, image recognition. And why might we want to do classification? Well, it's really important in various industries for decision making. You can use it for segmenting your customers, so telling if a customer is likely to buy some product or not. For detecting fraudulent activities, so you could say, oh, well, let's see if we can detect when a credit card is being used for bad reason. And so does anyone have an example of a classification problem? Send it in the chat if you do. But yeah, let's talk about decision trees now, which is one of the key algorithms for machine learning. And so decision tree, excuse me, is a flowchart-like tree structure, and each internal node represents a test on a feature. And so each branch represents the outcome of that test. And so think of this a lot like, and each leaf node, of course, represents the class label. So eventually you'll get to the bottom of the tree and have the label. But think of this like playing 20 questions. I don't know if any of you have ever played 20 questions, but 20 questions is a game where each question that you ask the person narrows down the possibilities, and then you guess at the end. So that's exactly what we're doing with decision trees. And decision trees, they work by splitting the data set into subsets based on the feature that yields the greatest information gain. So, here's some key terms for you to remember. There's first the root node, which is the top node that represents the entire data set. So all the data starts at the root node. And then a leaf node is another key term. So this is a terminal node that represents the final class labels. So that would be where you end up essentially after the decision trees algorithm has worked. And then branches are paths from one node to another. So you might follow some branch to get to your answer. And that brings me to the key loss function that we have for decision trees, and it's entropy. So entropy is a measure of the randomness of or impurity in the data set. And so the entropy is equal to the sum of 1 through n pi times log 2 pi. So pi, we might be asking, what is that? That's the probability of some class I. So at the beginning, we might just randomly be assigning the images to classes, and that would just result in a entropy, very high entropy, very random data. But then information gain, which we'll talk about next, is the entropy of that parent data set minus the entropy after the data set is split along some feature. So you could think of this as basically showing how the entropy is being reduced of the data set. So it's becoming less and less randomly organized over time. And nk is the number of samples in child node k, where n is the total number of samples in the parent node. So you can just see that in this equation. So you're summing across all of these different categories, calculating their entropies. And if the entropy of the new result is smaller than the entropy of the data set, of the original data set, you've had some information gain through that splitting. And so that's going to decrease the randomness of how the data is distributed, right? And so let's try an example, because it's kind of hard to do this without doing some example. You know, nobody likes to just look at the equations and that's it. So let's calculate entropy and information gain. And I have this table here for us. So we will use it to figure out whether to play tennis or not. So that's kind of the entropy here. So all right, let's start by diving into this, and I'm going to open up my my code pad. So let's see, open up my code pad. All right, and yeah, so in our code pad, we're gonna first calculate the entropy of the parent node. So the parent node, remember, is the entire data set. We talked about that. And first, we're going to count the total of instances. So count total instances. So we do have n equals 14 instances. And we'll count the positive instances. And let me see, I think I need to copy this table over, because now that I'm up here on the stream, I can see that we should probably copy this table over so that everyone can see. That didn't really work very well. Let's see if there's any way for me to paste in an image. I don't know. Yep, that kind of worked. All right. So if we look here at our table, can I change the scale of this a little bit? It's a little bit large. Let's see. Let's try this. Oh, that didn't really work. Well, let's just keep it the way it is. Maybe we can try this. Yeah, it didn't really work, but yeah, just puts it at the end. Well, that's all right. We can just make do with this table here. So if we count the positive number of instances, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we actually had 11 positive instances. And then, well, actually, let's see here. Let me just double check to make sure. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11. Yep, 11. So we could just say n positive is 11. And then we could say n negative is going to be 3. So those are the cases where either we went outside or we did not play tennis. So now we can calculate the probabilities. So we can calculate the probability that there was a yes. And that will just be equal to the number of positive instances divided by the total. And we can do the same for the negative. So that would just be number of negative instances divided by n. And so now we could calculate the entropy. So remember, the entropy is equal to negative PS times NP log 2 of PS minus NP P no NP log 2 P no. So, we should import our NumPy as well. So you might remember our equation. I'll put up the equation again. The equation is to sum the probabilities multiplied by the log base 2 of the probability. So we have to add across all instances. So n0 would be when we have the outlook being yes, and n1 would be when we have the outlook being no. So that's why when you look here, when we run that, we get 0.75, entropy of 0.75. So this is our parent entropy. And actually, I'm just going to call this E parent so that it's saved. Okay. And so now I want to calculate the entropy of, or actually, this is actually the entropy of, let's see here. Right, so let's split the entropy on outlook now. So we're going to calculate the entropy of the child nodes because when we split the entropy on outlook, we expect that the entropy will go down. Because if you can think about it, most of the time when it's sunny, well, I guess here, most of the time when it's sunny, we're going out and playing, and overcast certainly. And then when it rains, often we're not. So let's try and see if splitting by outlook actually does anything here. So for our outlook sunny, it looks like we have a question actually. Thank you, Joro, for sending that. The way you can earn swag, yes, is by completing these challenges. So thank you for sending along. And Joro asks, what's NP here again? So great question. Actually, I wrote NP would be NumPy here. So that's used to import some operations, some mathematical operations in the code. So for example, np.log2 would import the function log base 2. So hopefully that helps you all understand what's happening here. Yeah, no problem. Happy to help with that. But now we're going to split our data on Outlook Sunny. So remember, before the entropy of the parent node was 7.5. So let's see if it goes down when we do this. Okay. So you'll remember that the way we do this is we're gonna use this formula, and the right-hand side is where we're calculating the entropy of the different split samples. So let's start with sunny. And we know that for sunny, there were sunny instances. Let's just do sunny instances. How many were there? 1, 2, 3, 4, 5, 6. So there were 6. And then the sunny positive. So this is the total number of sunny days. And sunny positive will be the number of positive instances on sunny days. So this is the number of, let's just say, number of number of play tennis. Let's just say number of tennis days on sunny days. That makes kind of sense. Number of tennis days on sunny days. So let's go over here. Let's see how many tennis days were there. So none so far. Oh, there's 1 for sunny. There's 2, 3. So there's 3 sunny days that were tennis days. And then the rest, of course, will just be non-tennis days. So we can calculate the entropy of sunny, and it's just going to be negative. And remember, we have to divide these two to get the probability. So the equation here is sunny POS divided by sunny instances, just like we did in the top. We did n position divided by n, so that was just, or n positive divided by n, so we just did the positive instances divided by the total, multiplied by the log, minus the negative probabilities. So that's the entropy of the sunny. And let's do the overcast now. So we'll go to overcast and see. So we have 1, 2, 3, 4. Wow, looks like whenever it's overcast, the tennis player likes to play. I guess that makes sense. If you've ever played tennis, I don't know if any of you have played the game, but when it's sunny sometimes and you're looking up at the tennis ball, it gets in your eyes, the sun. It can be really annoying. So maybe people would prefer to play in overcasts. But anyway, so we had 4 cases where it was overcast. 1, 2, 3, 4, and every single time it was positive. So we can type the entropy of overcast, which will be the positive type cases divided by the total. And then the entropy for overcast is kind of interesting because we didn't have any negative values. There was no case where overcast resulted in not playing tennis. So we can just finish right here. And then there's one more that we'll get to, which is our rainy outlook. But we have a question here in the chat. So 404 says, I can't believe GHW is already over. I know, it's so sad for Global Hack Week to be over. But why did you go over why the temperature graph you posted in Discord has this weird alternating up and down pattern between years? I did not go over that, but the basic drivers of that change would be El Nino and other variability, natural variability in the climate. So the climate will just go up and down every year naturally to some degree. But in the background, there's global warming. So that's why that plot I showed in the Discord has up and down patterns. Yeah, we were doing some data visualization for people who didn't get to see. And yeah, so yeah, let's go ahead and yeah, it's kind of cool, right? So that's just what's happening there. But let's go ahead and calculate our next one. I tried to find, oh, there it is. I found it. I couldn't find the graph for a little while. Let me show that actually, just so people can see what 404 and I are talking about. It's a graph that we made for our global temperature anomalies. And yeah, you can see that there's some oscillation here. And usually the El Ninos will last for a couple of years and then switch to the next one. So that's why they kind of go up and down. And right now we're in La Nina, so we should be actually down in a down cycle, but strangely the temperature is very high. It's actually record high now. So yeah, it's a little bit concerning. But yeah, let's go back to our rainy days. So we have 1, 2, 3, 4, 5, 6 rainy days. So we can say that rainy instances will be 6. Okay. And of the rainy days, let's see, when we played tennis. One. Okay, so we played on this day. Yes. 2, 3. We played on 3. Let's see, 1, 2, 3, 4. We actually played tennis on 4 rainy days. That's kind of funny, because normally you wouldn't play tennis on a rainy day, but yeah, I guess this data set is not realistic. I should switch that around. But then, of course, we would have negative case where there's no tennis being played. That would be 2. Okay, and so then we'll calculate the rainy days using the same formula as before. And now we're going to calculate the information gain. And so this is where we essentially calculate the weighted entropy. So we're going to do first entropy splits. This is the entropy after the split. And we're going to calculate first the sunny instances divided by n. So it's actually a weighted entropy. And so of each child node. So with the sunny instances, we take the entropy of sunny and multiply by the fraction of sunny days in the data set. Okay. And then in the overcast case, we take the entropy of the overcast and multiply by the fraction of overcast instances in the data set. And then finally, with the rainy data set instances, we take the entropy of the rainy days and multiply by the fraction of rainy. Okay. And so that's how it ends up working out. Oh, someone said, can you send the this table? Yeah, sure. Sorry about that. I should have definitely sent that. Let me, you know what? I'm actually going to put all of this in a code share. Just give me 1 second to do that, because it would be way better, I think, if everything was in some kind of code share. All right, so here's the data set. I'll just paste it in the comments. And then I'll put it in code share too. I'll put all this in code share, actually. Yeah, I'm going to make this I think this should be better. So paste it all in. All right, and share this code share with all of you so that you can see. Thanks for sending that 404 too. Super helpful there. But yeah, now it's all in a code share. And so you can just copy what we've been doing so far. But yeah, so now we have the weighted entropy, E-split. And let's actually look at E-split. You know, I actually want to look at all of them, so I'm just going to make a new cell. I want to look at the sunny day entropy, the overcast day, the rainy day, and the weighted. So you can see that the sunny day entropy was 1 actually, which is quite high entropy. basically random. So you could see, look at the sunny. 3 of the days we played tennis, 3 of them we didn't. So that was a very high entropy day. And then we had the rainy day where we had pretty high entropy, but there was a little bit of an imbalance. So there were 4 days where we had the positive outlook and about 2 days where we had a negative. So it's less than 1. And then the overcast was key. I mean, the overcast was where we had basically all of the circumstances pointing to a less of a day. So to a tennis day. So when we do the entropy of the split here, we get a higher entropy than when we started. So if we print the information gain, which is the parent minus the split, we actually had a negative information gain. So it was not beneficial to split on these outlook days to when we played tennis. Now, if the information gain was positive, that would mean the entropy went down. And actually, let's try to split on whether it's just overcast or not. So if we split on whether it's overcast or not, let's see if that does any better than splitting on sunny, overcast, and rainy. So if we just say not overcast, and we'll say that not overcast instances, we'll say that this is just the sunny instances plus the rainy instances. And we'll just define the positive and negative this way. And we have our entropy. And then when we calculate the weighted entropy here, we should be able to see the information gain. Oops, messed up something here. Let's do this manually here. So the E not overcast, and it's going to be equal to minus of the not overcast positive divided by the not overcast instances. So that's the probability there. Not overcast instances. Okay, so it should just look like this actually. And I think that does it for our case here. And if we split just by the whether it's overcast or not, you can see the not overcast day entropy was quite low. Let's actually see what that looked like because we can't really tell from this. I want to print out the not overcast instances, the overcast positive and overcast negative. So it looks like when it was not overcast, we played tennis 7 times, and then we didn't for 5 times. So it's quite a few times that we didn't play tennis, actually. Whereas with the overcast case, you might remember that every time it was overcast, every time it was overcast, we chose to play. So the information gain was positive here because the entropy was reduced from the overall data set. All right. So we split on sunny and rainy and overcast. It doesn't really give us that much information. Actually, it does not really give us any information. But if we split just based on this simple overcast or not, we get an information gain. Okay, so that goes to show you that the decision trees, how the decision trees work, and how the splits can be important between the several codes. So let's actually copy these into the code share so that you all have it. This is our new overcast case. Oh, weird, I'm having some trouble connecting to the code share. Let's see. All right, hard to connect to the code share actually. I'm not sure why, but yeah, you could take a screenshot if you want to, but we're going to now do a decision tree algorithm in Python using the scikit-learn library. And we're going to use the iris dataset, which is a classic in machine learning. I think we did actually look into the iris dataset earlier for our, I think it was for our data visualization track, but we're going to look into iris dataset again. And what I'm going to do is just put it at the bottom here. So we'll do decision tree iris dataset. And we're going to import a bunch of stuff from sklearn. We'll import, let's see if these are right. Yeah, I'm just going to import them manually because I have a specific way that I want to import them to follow our guide. All right, so it didn't import GraphViz, so maybe I don't have it in this library. Let me get it installed for us. Sometimes you have to go into the terminal and install something new if your current environment doesn't have it. Just wait a minute for that to install. And it looks like it's installing, which is good. And let's try again, and it works. So we got our installations to work. Now we can move on to some of the fun stuff. So first, we're going to load in our iris dataset. And we'll say iris.data for X and iris.target for Y. So if we look at this iris dataset, just to give an example here, each of these datas, so we have the data key, each of these datas is giving features about the flower. So they're the sepal length, the sepal width, the petal length, and the petal width. So these are widths, measurements taken of the different leaves and stems on the flower. And then target, so that's this one here. Target is a 0, a 1, or a 2. And so these are the 3 species of flowers that we had, right? And so we can now split our data to do training and testing. And I think if you joined us for the vision classifier workshop in part 1, we did a little bit of this training and testing stuff. So, but if you weren't, I'll give you just a hint about it. So what we're doing here is separating the data randomly and putting, so we'll make a test size of 0.2. So 20% of the data we're going to put into testing. And what that does is it sets that data aside so that we can look at the data after the model's been trained and see if the model can recognize data that it's never seen before. So that's what this training versus testing split is about. And when we do this, it runs, and we can see that xtest is just a bunch of random data, and then xtrain is just the same thing, but it's going to be a lot more lines, right? So it's just randomly picking some flowers to hold away until after the training is over to see if our data set can recognize flowers that it's never seen before. Okay, and so the next thing we'll do is train our classifier. So we'll do CLF and we'll do decision tree classifier. And we need to give it some criteria to pick for its loss function. And we're going to use entropy. No surprise there, right? Remember, we calculated entropy just now of our playing tennis data set. And we used that as a criteria to say, when we do a split, did it increase the information or did it decrease the information gain? And we'll also put a max depth. So a max depth parameter tells the decision tree classifier how many branches it can create. So we don't want to make these decision trees have like 16 different decisions, because if we do that, we risk overfitting the data. And overfitting, you might have one decision tree that specifically handles one variable and just says, if it follows these 10 different criteria, then, great job. But yeah, we want to kind of make everything generalizable so that when we get to that testing stage, it doesn't have a bug, doesn't have an overfit. And so we'll fit the xtrain and ytrain data to this new decision tree classifier and just run this code. It should be pretty quick, actually. Decision tree is not a very slow algorithm. It's very fast for small data sets. And then, of course, if you actually have a much larger data set, the decision tree classifier would take a very long time. But for the purposes of just a simple small data set, it does not take that long. And yeah, we've now built our model. So we can use this model to predict and evaluate. So we'll use y predictions, and we'll say y predicted is clf.predict of xtest. So when we evaluate the model, I'm just gonna say this is training the model. Let's put all the training in one step, actually. Or I guess it already is. So this is training the model. This is prepping the data, I guess you could say. Put this all in one. It's training the model. And then here we will test the model. And so we make the model make a prediction for each of these test data based on their features. And then we will calculate the accuracy using the accuracy score method. Remember, we got that accuracy score from the sklearnmetrics library. And actually, I'm going to show you the accuracy score just so that you all can see what it is. Let's see here. Yeah, so if you look at this accuracy score on this website here, hopefully you can see that, but it's showing that the accuracy score is just computing, it takes in the ground truth of the labels, the predicted labels, and it'll just return the fraction of correctly classified samples. So it just says, of these flowers, what fraction of them was classified correctly? Okay, so let's go back to our code pad. And we can apply the accuracy score. We're doing it for that testing data, if you remember. And yeah, why don't we now print out the accuracy just to see how accurate is our model. And it says accuracy of 1, so actually that's perfect accuracy. Amazing. I doubt we'll always get an accuracy of 1 though. Oh, maybe we do actually. It seems quite surprising, honestly. Let's see if we make our test size larger. Yeah, so if we make our test size larger, we get a lower accuracy, but that's kind of amazing, actually. If we have enough data, we get a very, very accurate model. So yeah, awesome. So we got super, super good model, and evidently we should check out the tree. Let's see what this tree looks like, because my goodness, I mean, if we have such a nice accuracy, we should definitely see what this looks like. So let's visualize the tree, all right? And we're going to use this graph viz that I was mentioning earlier. So we have CLF, which is the classifier model, the out file, so what the output would be, and then we'll just type in some keyword arguments to show what are the features, what are the classes. And then I'm just going to add some parameters to tell a little bit to the method what I'd like the graph to look like. And then you just say graph equals graph is dot source dot data and render. So we'll render the iris decision tree, and let's see what we get. Oh, I think this might be an issue with the installation of GraphViz. All right, let's see. I'm going to try this on my Google Colab subscription. That's where I always go if there's any bug. I saw another bug with the 3D interactive stuff for Plotly, actually. So I think there's something wrong with I must have broken something in my computer. But yeah, let's go to this Colab notebook. Mm-hmm. All right, I got the Colab notebook up and running. So let's try it out. All right. Hopefully you all can see that Colab notebook. I'm going to shrink it down so that it's a little bit more visible. All right, so let's just copy some of these codes into the Colab notebook. Just bear with me while I do this. We'll connect, I don't know, we'll just connect to some random CPU. Doesn't really matter for this one. We don't need an A100 GPU to run this. Unlike our Vision transformer that we had before. But yeah, let's see how it runs. If we get it to work. We'll hope it does. All right. It looks like it did output our decision tree. We can look into the... Okay, and here it is. I hope you all can see that. But here's our decision tree. This had a 100% accuracy. If you look at the... Amazing. You won't see that too often. 100% accuracy. Oh, I have a question in the chat from defendant, actually. What is the random state? I can't quite see it. So that's a good question. Let me scroll up and show the random state. Actually, I'm just going to update the code share too before I show you that. So let me just quickly update the code share. I was having trouble. Oh, yeah, I got a timeout from the code share. That's lame. All right. Sorry, I put the code share. I put it in the code share, the decision tree stuff. But the random state is pretty much not needed. But what it does is it makes sure that when you split the data by 20%, 80%, remember I said it was random, and it is random. But when you choose this random state variable equals 42, what you're actually doing is ensuring that that it doesn't do a new random split every single time. So a lot of the times, if you want to be able to reproduce the code, you're going to take this random state and you're going to specify some variable so that other people can reproduce the exact results that you got for your analysis. If you don't specify that random state variable, then every time someone else tries to run your code, they're going to get a slightly different answer because their split was different. So that's what the random state is for. That's a good question. But yeah, let's look at our decision tree now. So, all right, so the first case we have here, we have a node that we're going to take all the data through. It's this top node here, and it says petal length is less than 2.45. So if the petal length is less than 2.45, every single time the class was Setosa. All right. So we chose Setosa for our leaf node here. But, or sorry, this is if it's smaller than 2.45, right? Less than or equal to. But if the petal was bigger than 2.45, we would go false, right? And so then we have to ask, is the petal less than 4.75? And so if the petal's less than 4.75, then we went to this side, this left side, and said, is the petal width less than 1.65? So this would indicate a very long but narrow petal. And if that triggered, then we would get versicolor every single time. You can see that. Because entropy 0 means that every single time it becomes this leaf node. And then over here you see entropy 0, samples 1, value 001, Virginica. So this is just one of these was a Virginica. You could debate, is this real? I mean, this node here, this leaf node, because it's only one sample and it's just saying, oh, well, we did find this one case where the Virginica was less than this petal length, but we needed to figure out how to get it away from the versicolor. So you could argue that this might not be a very physical node. But when you go to this right side, this is the case where the petal length was quite small, less than 4.75, but remember, it's going to be bigger than 2.45, so it's this kind of middle petal length. And then we say if it's a really big petal, really wide petal, then it's going to be Virginica. We change from versicolor to Virginica, and then most of them go on to be Virginicas if the petal width is going to then be quite narrow. But some of them, if the petal width is large enough, greater than 1.75, we go to versicolor. All right, so that's how this decision tree algorithm works. Okay, so hopefully that's helpful there. And let's just do a new data. Um, let's use our trained model to predict the class of a new iris flower. And this flower has the following features: the sepal length of 5, sepal width of 3.6, petal length of 1.4, petal width of 2.2. So I'm going to type that into the chat because I want to pull up our tree. Okay, so here it is. Here are the 4 numbers. And if we go back to our table, let's try to work through this table together. So we scroll up to the top and we see that the petal length, the first question is the petal length less than or equal to 2.45? Well, our petal length is 1.4. So that's going to bring us to true for this. And it means that we'll have a setosa. All right, so this should be a setosa flower. All right, so does anyone have any questions about these decision trees? We're going to move on to the k nearest neighbors algorithm, which is another classifier. But why don't we just take a quick, I'm going to take a quick few seconds to see if anyone has any questions. So, all right, let's say we don't have too many questions about the decision tree. So why don't we go ahead and go to the k nearest neighbors algorithm. All right, so k nearest neighbors is another classifier, and it's a basic instance-based learning method. And so it'll classify new instances based on similarity measures. And so the similarity measure is as follows. It's given a value of k, so that's k nearest neighbors, remember. The algorithm finds the k closest training examples to the new data point and assigns the class by a majority vote. So let me show you an example of this. Let's see here. I love to go to the Wikipedia images because they're so good. They always have a very clear example. So here's the example from there. And I'll zoom in a little bit. But you can see that the new point here is this green point. And we're trying to figure out, what kind of point is this? Should it be a red triangle or should it be a blue square? And so what we do is we just draw a circle around the k nearest neighbors. So in the case of this solid circle here, that would be if k is equal to 3. So if k is equal to 3, we look for the 3 nearest neighbors, and then we say, of these 3 nearest neighbors, which one has more, blue square or red triangle? And we see that it's red triangle, so we would classify this green dot as a red triangle. But then the dashed circle is a case where we're using 5 nearest neighbors, so k equals 5, and that blue circle becomes that green circle, becomes a blue square. So you can see how this k nearest neighbors algorithm might work in practice. And there is a way to calculate this nearness that we are talking about. It's called Euclidean distance. And it's named after Euclid because Euclid came up with the XY coordinate plane. So just a fun fact there. But you're going to use this distance metric to calculate how far away the neighbors are from the point of interest that you have, right? So let's look at this problem. So we have some manual KNN classification coming up here. And so given the following 2D data points, so they'll go on the XY plane, we have some class A, which is red, and some class B, which is blue. Let's classify the point 5, 5, and we're going to use k equals 3, all right, for this one. So let's actually go into our CodePad. Maybe I'll use our Google Colab now, because I'm kind of upset with my local machine. It's not treating me very nicely. So let's try that. All right. So we'll scroll down. And actually, I'm tempted to just share this Colab with all of you so that you can check it out yourselves. I'm going to share it with you all. And so you can see that yourselves. But yeah, this is going to be the next one here. So the distances to each point, we'll calculate them using d. So remember, d is equal to the square root of p minus q squared. Or excuse me, we'll do x1 minus x2 squared plus y1 minus y2 squared. And so we'll just say square root of, and let me copy and paste our classes here too. All right, so we have d equals np dot square root, and we'll just use 5 minus 1, so that's this first one here. Oh, right, we have, I'm going to put my, my new data point. So 5 minus 1 is the x equals 5, and the x equals 1 for this first red point. And then let's do the next one. So the next one is going to be squared, 5 minus 2 squared. So that's this this 2, 5y and 2y. So that's this first d, and I have to define numpy again. I guess I didn't define it already. But there it is. And so we'll run that one and just print out d. So there's the distance. And then we'll do the same, but now we're going to do it for 2, 3, comma 3, this next red point. Here's the next red point. So do 2, comma 3, print that out. And then we'll do, oops, keep getting that annoying thing. And then we'll do 3, comma 1, which is that third one here. And we get 4.47. So these are the distances to the 3 A points. So I'll say these are the distances to class A points. All right. And now let's do class B points. So I'm just going to put a new code here, class B points. And we'll just say 6, comma 5. So 6, 5, that's going to be 1. And then we'll do another one. So we have 7, 7. That's a distance of 2.82. And then we have 8, 6. So 8, 6 would be 8, 6, and we get 3.16 distances. All right. So I'm going to make this a little bit nicer here. We're going to say dB1, dB2, just to list all of these out. dB3. I'll delete some of these old things. Let's clean everything up a little bit in my editor. So DA1. And then DA3. So now, when we run, we get these 6. And I'm going to put them all into a list called distances. So I'm just going to put them all in. And here they are. And so then I'm going to put the classes here too. A, B, B, B. And we can even use a library called pandas. So use pandas to make a data frame where we put the class and the distance. So here's our data table, and that's kind of cool. You can just see, like, I've never seen that actually. Okay, well, here's our data table, and we can now sort by the column. So we'll use dot sort values. So where is it here? We can do dot sort values, and we just give it some by, and we'll sort by distance. All right, so now we can see what are the closest points to our value, okay? And so the closest points, it looks like they're all going to be from B, and the A's are all quite far away. So if we did k equals 3, we're going to just pick these 3 here, and based on those 3, 100% of them are B, classified as B. So hey, we're done. We have our answer, and that means that our new data point will be classified as B. And we could even look at this visually. So if we just plot, so we can do, let's just grab matplotlib, our trusty matplotlib, and we'll do scatter plot for, let's do the first 3 distances. So those are those first 3 classes, those first 3 which are going to be A. And we'll just call them red, use the label A. And then we'll do the next 3, which are going to be B, and we'll call them blue. So, yeah, I have to actually write these out. So, we can't use distances. Sorry about that. I forgot about that. So these are our X values. So 1, 2, 3, 6, 7, and 8. Actually, let's just put them XA. and XB. That'll be easier. XB would be 6, 7, and 8. And then YA will be 2, 3, 1. And YB will be 5, 7, 6. And so we run that, and let's type XA, YA for A, and XB, YB for B. And here's our data. And so we had this new point that we tried to categorize. Oh, and why don't we use our, we can make this exactly like the example on Wikipedia. So we'll do this, and then we'll say, or actually it was a square, I think. Not sure how to do square. Yep, it's a S. So, and then we'll do our 5, 5, which is our green case there. We'll just say X. We'll just call this X. And then we'll put a legend here. All right, so there it is. And we're trying to see, is this green point closer to A, or is it closer to B? And it looks like it will be closer to B just visually. But we, of course, also know now from our k-nearest neighbors algorithm that when we sort and we classify, we get a classification of B when k is equal to 3. The only case where we would not get a classification of B is if we had a k equals 6. But I think even then, we would probably just have more data. So that would not be an issue. All right, so there we are with our k-nearest neighbors example. And we're going to do a little more live coding where we implement KNN for a massive data set. So we're gonna do a breast cancer example. And so what we'll do is we type from sklearn.datasets. We'll import this load breast cancer function. We're gonna, I know we already have this in, but I just want to make the example complete. So we'll just do a train test split. And believe it or not, sklearn has its own k-neighbors classifier. Okay, and then I'll import our other things like accuracy score, confusion matrix, and I'll tell you what a confusion matrix is too, and classification report. But these are the libraries we'll use. And now I'll say, let's load in the data. Why not? So we will start by loading in the breast cancer data set. And we'll say cancer.data, cancer.target. And so X, these are a bunch of features from the Wisconsin data set. And so I'll show you this actually. It's a machine learning diagnostic data set. And let's see here. Here it is. So each of these real valued features are going to be things we'll look at when we're trying to predict whether this cell growth is breast cancer. And so we have a radius here. So that's the mean of the distances from the center to the points on the perimeter. We have a texture, so that's the standard deviation of the grayscale values. There might be some perimeter, some area. smoothness, fractal dimension. So very specific data about this tumor, or this potential tumor, I should say, this potential growth. And that's what we're seeing in our data set too. So let's go back to this here. And so we're seeing in X all of these perimeters, area, fractal dimension, things like that. And the target is going to be 0 or 1. Really simple. Is it a cancer growth or is it not? And so we're going to use our KNN classifier to do this. And first things first, we're going to split the data into training and testing data. And we'll just give it some test size. So we'll say test size equals 0.2. And we'll do a random state as well. Oh, I wrote tryin. That's not right. Train. Good thing we didn't go any further. And then we'll do KNN equals K neighbors classifier. Say the number of neighbors is 5. And we'll just fit this now. We can fit it to our training data set. Okay. And so now when we do our prediction, you can see the accuracy. I doubt it's going to be 100% accuracy like our iris data set, but we'll see. All right, so we get 95% accuracy. But we might want to know a little bit more about this. Where is it going right? Where is it going wrong? So we can use the following: confusion matrix. And we also have a classification report. And I'll explain what these are when we see them. Which we're about to see. So you can see that there is some confusion matrix, and it has a 2x2 grid. So in the rows, these are the 0 and 1 of the actual data, and in the columns, they are the predicted data. So in the rows, you could see, for example, this first row 0, this is a case where the cancer was not present, and 5 times the algorithm said that it actually was. So that's a little bit of an error. But fortunately, there was no case where the algorithm identified it where it wasn't present. And so you can see some of these classification reports here too, on the accuracy of the algorithm, on precision, recall, things like that. So we can actually tell. And if you change the value, we can just experiment. Why don't we change the value of K? Because it's not necessary that we use 5. What if we used 3 here? Well, if we use 3, we actually got a worse outcome, only 93%. And now if, let's say we did 10. All right, 10 actually gave us much better than 5. So it looks like having more in this case was actually a little bit better. And I wonder what the optimal one is. Well, we can actually test that. We'll just loop through these. So let's just do a little loop. I'm going to test several values. Let's just test 1 through 20, or 2 through 20, because we wouldn't, well, I guess we could do 1. And then we'll just print out the accuracy score for each case. And so you can see that the best accuracy seems to happen around 11 or 12. So if we go into 11, let's just try 11 and see how good that is. We got an accuracy of 0.98, and the confusion matrix was awesome. We only had 2 misses in the whole entire data set of about 100 plus things. So we're going to talk a little bit about these because I want to make sure that you all, understand them. So just a bit on these classification reports that we did. The accuracy is that ratio of the correctly predicted observations to the total observations. So it's just going to be how of these observations, how many did you get right? Okay, and then the precision is the ratio of the correctly predicted positive observations to the total predicted positive observations. So that's going to be of all of the predicted positives, where you said, okay, yes, this is cancer, how much did you correctly identify that? And then recall is the ratio of the correctly predicted positive observations to all of the actual positive observations. And then the F1 score is the weighted average of the precision and the recall. So you're sort of taking into account when, how frequently does this identify a false positive, right? So that would make the algorithm less precise. And the confusion matrix, as I mentioned, it has this predicted columns and actual values on the rows. So with our breast cancer case, we were getting some instances where the actual result was a negative, but the algorithm was, or the actual result was a positive, the algorithm was a negative. So that was the case that we saw. And so we calculated all of this using our reports, actually. But I want to mention now overfitting, which we talked about in some of the previous parts. So it's when a model learns the training data a little bit too well, and it results in some bad generalization to the new data. So you could have some high accuracy training, but a low accuracy test. And you can use something called k-fold cross-validation to atone for that a little bit. And so we're going to actually implement K-NN algorithm for another data set, but we're going to use some modifications. Okay, so let's try that. So we have our data set here, and we're going to now do k-means k-fold cross-validation on this. So I hope you all can see the table here. And so we'll say from sklearn.datasets, import load wine. And I'm also going to just import from sklearn model selection. we're going to import the cross-val score. Okay, so the way that you calculate the cross-val score, it's really simple. So I'm just going to load in this data set. So we'll do wine equals load wine. And we'll check out this, this data a little bit. Oh, it looks like I forgot to run that first cell first, but yeah, so we have some properties of the wine, and let's actually take a look. What is this wine data set? So here's the table showing you what that wine data set looks like. It's going to have several attributes, some flavonoid, malic acid, some of the taste of the wine, and we're going to have to guess what kind of wine it is. So there's 13 of these numeric attributes. It's 178 wines, and then these 3 show what region the wine is from. Okay, so let's try and take a look at these in our code pad. Remember, we had all these wine properties in X, and then in Y, we should just see the 3 regions. So there's 0, 1, and 2, okay? So I'm just going to simply copy our code from the previous case where we split everything into training and testing, and we did our KNN classifier here. And maybe I won't use 11 neighbors this time. Let's see, I don't know, maybe it'll work good if we use 11 neighbors. No, it'll have 7, 5, that's not that good. Let's see, can we do better? Oh, actually we did worse if we use less. Okay, well, maybe it's not quite as accurate as our breast cancer case, but we can test the validity for overfitting. We can test that using cross-validation scores. So what we do is we type scores equals, and remember we imported cross-val score. So cross-val score accepts 3 main arguments. So it's going to accept the model itself. So we had our KNN model. And then we did X and Y. And so if we look at the scores here, you can see that when we split our data into 5, sometimes the accuracy was lower than 0.75. So sometimes we got higher, like 0.8, sometimes we got lower. And so this is showing us how sensitive our model configuration is to the data that is present. And so Yash says, what's going on? Oh, good question. Well, just checking out some of these k-fold cross-validation stuff. We're actually, I guess, pretty much finished with our stuff for today. So we looked at the k-fold cross-validation, and now we're going to check wrap up. So we did explore some classification problems and their importance. We learned how decision trees work. We actually implemented the math behind them and implemented them even. And then we understood the KNN algorithm and applied that to some data sets. And we finally discussed the evaluation metrics and the overfitting prevention strategies. So yeah, if anyone has any questions, please let me know. I put all the code into the code share. So if you want to reproduce this for yourself, check the code share. Yeah, I actually realized I didn't update the code share with the latest stuff. So let me go ahead and update it. I'll show you all where I have the code share. So it's over here. So let's see, where did we leave off with the code share? We left off with GraphViz from the Iris data set. So I'm just going to dump some of this decision tree stuff in. So here's all the decision tree stuff while we're waiting for any questions that people might have. And then here was the KNN stuff. Where we did our breast cancer detection algorithm. And then we did confusion matrix, classification report, some of these classifier results for different N values. And then we did our wine data set finally, which we did for cross-validation. So we saw how we could apply the cross-validation to prevent the overfitting. All right, so now the code share is saved again, so you can all check that. But it looks like we didn't get too many questions, so we will leave it there. And hope you all have a great rest of your Global Hack Week. I think the end of this is pretty much happening right now, actually. I think Mary and Ryan will be on soon to give some final calls on here. But yeah, so defending, yes, do you work in research? That's a good question. So I do, actually. I work in research as one of my full-time jobs. So yeah, thank you, Jasper. I saw you in some other streams, so it was great to see you around. I love your profile picture, by the way. I wonder if that's a real bunny or if it's a AI bunny. But yeah, I'm happy to connect with folks on LinkedIn after the workshop. Yeah, honestly, Defendant, if you want to talk a little more, please connect with me on LinkedIn. I'm happy to discuss about stuff like that. So yeah, definitely give me a connect on LinkedIn, and I'll answer some of those questions. But yeah, all right. Thanks again, everybody, and hope you have a great rest of your day.